Thanks for joining for the last lecture. Like, this isn't all there is for the three-body problem, but I think this was sort of like a dry run for an actual course on the three-body problem that maybe I'll try to implement as an actual course at Virginia Tech sometime in the future. But I think it's been fun. We've learned a lot. Today, we're talking about halo orbits. So these are the three-dimensional orbits that have been on people's minds recently because of the James Webb Space Telescope. So we'll talk about how to compute them and then go through a little MATLAB tutorial. And then that'll finish us up. So this is sort of our foray into the three-dimensional problem. So for this, because there's a lot of equations, I'm just going to be using some slides, but I'll annotate. So just to say a little bit about the importance of halo orbits, the thing that got me involved was looking at this Genesis Discovery mission, which was a halo orbit around the Sun-Earth L1. So about 1 million miles in the direction of the sun is L1. And this was a pretty large halo orbit where it was a transfer from low Earth orbit, and you get a natural transfer if you go on the stable manifold. So this red segment here. So this is the Earth, and then this is the segment that's going to the orbit. And then it gets on the orbit just naturally. And so you get several 2D views and then a 3D view. That's, I go to the next one. There's also been interest in using orbits around L1 for studying space weather, which some people at Virginia Tech are very interested in this, in particular for L1, because it's outside of the magnetosphere. It's far enough ahead that you could look at solar effects before they reach Earth. So NASA has interest in this. The first mission that was sent onto an L1, Sun-Earth L1 halo orbit was IC3, launched in 1978. It monitored solar wind and other things. And this is an idea of the orbit. This is all in units. I don't even write what the units are, but all these units down here, it's 10 to the 5 kilometers. So this is something that had what we would call an AX amplitude, and then there's an AZ amplitude. And they're not independent, they're actually related. So, all right. Another mission concept that was going to use L2, Sun-Earth L2, was called the Terrestrial Planet Finder. As far as I know, this isn't happening anytime soon, but it was a mission concept where there was going to be formation flying of 4 free-flying spacecraft at around a halo orbit at L2. In fact, each of the individual trajectories for the spacecraft wasn't going to be on the halo orbit itself. They were going to be on something called a quasi-halo orbit. So this gives an idea of what a quasi-halo is. So instead of being one periodic orbit, it looks like a torus that's sort of winding around that periodic orbit. So you could have several things. This is showing kind of 6 trajectories going around a quasi-halo orbit. Let me show. I think I've got a video somewhere of one of these. So this is a simulation and artist rendering of what was going to be happening. That main orbit is the halo orbit, and then these are different formation flying vehicles that are kind of moving in a plane. The idea here was if you have multiple telescopes, they could combine their signals so you can get a very large baseline, just depending on how far away these telescopes are. So one of the challenges was, how do you get all of these to be in the same plane? How do you reorient them optimally to move and point at certain parts of the sky? So that's what that yellow arrow is. That's the part of the sky that it's aiming at. And yeah, that just sort of shows that. So this was some work that was done almost 20 years ago. There's also an orbit. This is called an almost rectilinear orbit. It was recently launched. It's called CAPSTONE, and it's related to cislunar autonomous something. But it's sort of like a first step to try to get GPS on the moon. So this is what the trajectory will look like when the vehicle actually gets into orbit. It's this is called a almost rectilinear halo orbit. And so it seems to be orbiting the moon, but it's really in some interesting 3D orbit where it could have the normal to the orbital plane can almost be pointing at the Earth. And so we'll see how that progresses. Each of these orbits, I would guess, is about a week. So that's CAPSTONE. And then, of course, we know about James Webb. So this is the James Webb halo orbit, the thing on the right. So this is seen from the side. If we look from the top, so viewing above the ecliptic, that's the halo orbit. And I don't know where the current location is. They're showing L plus 2 days, L plus 180 days. This one that's highlighted is L plus 200 days. It's launch plus 200 days. So we might even be able to compute this orbit. That's what we'll try to get to at the end. All right. Let's go to here. So the 3D equations of motion in non-dimensional form, we've already derived them. So this is what they look like, just written in that second order form. Here, U bar is the effective potential. And I'm using capital letters because I'm going to reserve lowercase letters for something else. So for doing calculations around L1 or L2, we now want to be more careful and do it in a way where we can look at terms beyond just linear. So let's say, for example, we want to look at the equations for a satellite in the vicinity of L1. So we're going to translate the origin to L1, and we're also going to scale things so that a distance of 1 now corresponds to the distance between L1 and the nearest primary mass, which is M2. So we are rescaling. I can draw here. Instead of saying that the distance between M1 and M2 is 1, which is what gave those original equations, we're now going to say that the distance between L1 and M2, that equals 1. Before we called that either gamma or gamma 1. So that's why we're writing gamma. That's the distance between M2 and L1, and then we're dividing by gamma in all of the directions. So in this new coordinate system, we're using little x, y, and z. There's also a new time variable that we introduce, and it's going to just scale as gamma to the 3/2. So we're doing all this so that we can write the equations in a nice way. And one thing that shows up is those 1/r potentials. So I don't know if you've seen things where you can write 1/r potentials using Legendre polynomials. These things, Pn. So we're writing out the linear part on the left-hand side here. This is the linear part. And for the right-hand side, we would usually just write 0 if we're only looking at the linearized dynamics. So this is where all the nonlinear terms are. But now we're going to keep them. And we'll make them, we'll write them in terms of Legendre polynomials. So there's these terms or these constants Cn, and Cn, it's a function of mu and gamma. And then also n, which is an integer. So this is a sum of terms, n from 3 to infinity, or as high as you want to go. So C2 is actually the same as mu bar that we used from an earlier lecture. and C2 is greater than 0. And for the Sun-Earth L1, I'm just showing some of these first few constants. So C2 is around 4, C3 is around 3, and then C4 is around 3 as well. So what are we going to do? Well, some initial work several decades ago was looked at analytical ways to approximate halo orbits. And to actually see when halo orbits come about, you need to get a higher order approximation than just linear. So there's a third order approximation that was first done by, the first one I saw was by Richardson, and he used something called the Lindstedt Poincaré method, which I'll say a little bit about, but I'm not going to go into great detail. I'm just going to say there is a method if you're looking for a periodic solution in some autonomous ODEs. Autonomous means the equations are of the form x dot equals f of x. Then if you have some maybe geometric insight that there should be a periodic orbit, then this Lindstedt Poincaré gives a means to find it. And we have to look at nonlinear terms to get halo orbits. Those Lyapunov orbits show up with just linear terms, but the halo orbits show up as a bifurcation for sort of larger and larger Lyapunov orbits. So once you get to a large enough amplitude of Lyapunov orbits, two other families that are three-dimensional and sort of come out of the ecliptic plane bifurcate from that Lyapunov orbit. So once we have an initial guess for an orbit, we'll use differential correction just like we used for large Lyapunov orbits in a previous lecture. All right, so just looking at the linearized equations, so the right-hand side now is 0. At least the first two look exactly like what we treated before when we were just looking at the planar problem. And now this z direction, because C2 is positive, this thing is just simple harmonic motion. And it doesn't depend on x or y. So the x-y dynamics are coupled, at least in this linear approximation, and then z is uncoupled. So for this set of equations, we get 6 eigenvalues. We're going to have a purely imaginary pair that corresponds to the z dynamics. And then we'll have a purely real pair and purely imaginary pair that corresponds to the xy plane or the horizontal dynamics. So for those ODEs, a general solution is going to look like this. So we've got x and y, which will have a frequency of the omega p. And then the z dynamics will have omega v as their frequency. And I'm showing some values for the Sun-Earth L1. Omega p is 2.086, omega v is 2.015. Notice they're not equal, but they're close. And these amplitudes, AX and AZ, they specify the in-plane and out-of-plane motion. So AX gives us basically the X amplitude. That's actually Y. Sorry about that. How do I get rid of that? There we go. So this is AX, and then AY is just going to be kappa times AX, and then AZ can be picked separately. So a general motion is going to look like this. It's called a Lissajous pattern. So it looks like it's different sines and cosine winds with different frequencies. So the general motion for this linear system is going to look like this. It's called Lissajous pattern. To give you an idea of what it looks like in 3D, this is it. So it looks like, right, looking down the XY plane, that's this first projection down here on the lower left. So that's looking down here. So it looks like we've got motion sort of going around the outside of some, this looks like some kind of car part that's like an extruded oval, and you'll just have trajectories kind of winding around on it. Now, if the frequencies were equal, then we get a halo orbit. They're not equal because we're only looking at the linear approximation. But as you go to, as you look at larger amplitudes and consider nonlinear contributions, you can get to the point where the frequency of the in-plane, the planar motion, and the vertical motion is equal. So, for example, that IC3 halo orbit, it had a Z amplitude that was about 110,000 kilometers, and then AX was about 200,000, and AY about 600,000. And again, though I'm not writing it here, all of these units are in multiply by 10 to the 5 kilometers. So multiply by 100,000 kilometers. So L1 is at the origin here, right? L1, L1, L1. Okay. So I'm saying even though in the linear approximation, those frequencies aren't equal, the frequencies will actually change as you include nonlinear terms. So we'll use what's called the Lindstedt-Poincaré procedure. This is where you include higher order terms. So before we had just the linear part, and we were setting that equal to 0. So this would be the X, Y, and Z equation, the left-hand side. Now on the right-hand side, we're including those terms that were related to Legendre polynomials and including them up through order 3. So this term, say, these are all, I would say, order 2. They're second order in those parameters X, Y, and Z. And then this term, because we have an X out in front, X times X squared, X times Y squared, and X times Z squared, these are all order 3 terms. And then we just ignore order 4 terms. So for bookkeeping purposes, we just put this 04 so we know, okay, we've gone up through order 3 explicitly, and then there's order 4 and higher that we're not going to care about right now. So we're considering the second order and third order terms. And we're going to try to get a periodic solution here. So going back to just the linearized equations that, remember, had this form for their general solution, we're going to set the frequencies equal. So we want omega p and omega v to be equal. We're going to just assume they're equal and apply the Lindstedt-Poincaré method. So what are we doing here? We're writing things so that the Z dynamics, we're just saying that the Z dynamics will have a frequency of omega p, which was the frequency of the planar dynamics. So we're imposing this. So we're imposing that the solution has periodicity with a frequency of omega p. Now, for bookkeeping purposes, we're going to have to take this into account somehow. So if we go back to the Z equation, this is what we just wrote up here, but we're including this term that takes into account that there is some difference between omega p squared and omega v squared. So we're just calling that delta. So this is delta times Z. So these are the nonlinear terms. And now we're including another linear term. So Richardson, in a paper that I can give a link to, but we have most of the results in chapter 6 of the book. Like I said, he's developed this third order approximation. He uses the Lindstedt-Poincaré procedure. What the Lindstedt-Poincaré procedure does is it introduces a new time variable, tau, where tau is scaled by some kind of frequency or frequency connection. And here we're saying that omega is 1 plus other things. So omega is 1 plus omega 1 plus omega 2 plus omega 3, etc. And these are going to be expanded in some term. So omega 1 is assumed to be something of order AZ. Omega 2 is assumed to be something of order AZ squared. Where we're using AZ in the normalized units, where distance between the Lagrange point and the secondary mass is 1. So AZ, we're assuming, is something smaller than 1, typically much smaller than 1. So it's playing the role of some small parameter. And that's what the Lindstedt-Poincaré method needs. So there is more to this Lindstedt-Poincaré method, but I have that in a separate video. I just don't have time to go through it here. I'll provide a link to that video. So now when we use this new independent variable with omega, and we haven't specified, right? We've got omega is 1 plus omega 1 plus omega 2 plus omega 3. We don't know what omega 1, omega 2, and omega 3 are yet. Those are solved for as part of this method. But taking the derivatives with respect to tau, that's what this prime means. So x prime means dx d tau, etc. And the equations basically look the same. We start by introducing a solution that looks like this down here, where we replace t with tau. So everywhere that we had t, we're now putting tau. Notice the frequencies are all the same. We're saying it's omega p. It's the frequency of the horizontal motion. We want the frequency of the horizontal and the vertical motion to be equal, because that means there's periodicity. So just some highlights of what the method does. We're going to look for solutions that are of this type, where x, y, and z have coefficients that will be solved for. And then we're going in higher and higher powers, or cosine and sine n tau 1, where tau 1 is omega p tau plus a phase. And if you go through the Lindstedt-Poincaré procedure, you find that omega 1 is 0, but then omega 2 is non-zero. It's actually second order in the frequencies. So we're going to have a omega, which is 1 plus, to leading order, we have omega 2. And that'll be high enough. So we're removing what are called secular terms. This is what Lindstedt-Poincaré does. If you were to do what's called a naive approach to getting a periodic trajectory, you'll end up finding things that are called secular terms. Those are things like xt is t sine t. T is going to grow without bound. So this isn't going to be periodic. So you need to get rid of anything that's got like t or t squared. Anything that's not periodic in t has to go away. So as part of the procedure, what you find is that there's a relationship between the x and z amplitudes, as well as that delta parameter. And so L1 and these little L1 and little L2 are constants that can be calculated. And I've got all those details in section 6.6 of the book. So Richardson's third order solution, we're not writing the ODEs anymore. This is what he found as the solution using the Lindstedt-Poincaré method, is this. So we've got x, y, and z, and it's all periodic in time. And it also has two solution branches. And it depends on whether this m this integer is either 1 or 3. Later we'll interpret that as we call these either northern or southern halo orbits. So like they spend most of their time either above the ecliptic plane or below the ecliptic plane. And here they are shown. So for m equals 1, we get a positive z amplitude, and that's called a northern halo. So that's what this upper grouping is. Seen from above, and I think this is for L2, in fact. This is L2. Seen from above, they look the same, but these top two, these are the northern ones. You see it's kind of spending a lot of time above z equals 0. And then these are the southern ones. So there's these two types of halos, and they're symmetric. They're mirror images across the XY plane. For halo orbits, you can't pick the amplitudes independently. So they are definitely related one to the other. What's often done is you just write things in terms of the AZ amplitude. So a halo orbit can be completely characterized by the AZ amplitude because there's a relationship. So this is showing the relationship between the amplitudes. I think this is for the Sun Earth L1. And these are in units, again, of 10 to the 5 kilometers. So you can see that for an AZ that's really close to 0, we have definitely a non-zero AX. So the halo orbits only show up when you have a pretty large AX amplitude. There's also a relationship, and you can compute it for the Z amplitude and the period. So this is showing the period in days for a Sun-Earth L1 orbit. And you notice they're all pretty close to each other, around 177 days. That IC3 halo had a period of 177.73, and it's about here. So we could read off what that Z amplitude was. It was about 100,000 kilometers. I think what I wrote, it was 110,000 kilometers. So though that gives you, that's good analytical insight that gives you an idea of these periodic orbits. If you were to try one of those initial conditions that you get from the Richardson approximation and integrate it for one period, it's not actually going to come back onto itself in the full nonlinear system. So what you do is you do differential correction. You say, I've got a good initial guess. And just like we've talked about before, this is an iterative process where you change the initial conditions to lead to the final conditions and the initial conditions matching up to within some tolerance. And using symmetry, I don't quite do that. I'm going to call this is the XZ plane, and we'll have some initial condition, and it'll come back, and we're just looking for it to come back and be going exactly in the y direction. So the initial velocity is only in y, and then the final velocity is only in y. So just to give you an idea how you do differential correction in the 3D circular restricted three-body problem. Now let's go back to those usual equations, and now the little x, little y, and little z just mean the usual non-dimensional form that we've been looking at. And we've said things about this before where you want to get the variational equations. They're linearized equations around some kind of some kind of reference trajectory. So if I have some reference trajectory, I'm calling x bar t, and I want to know what happens to small variations, delta x bar. I want to know how those evolve in time. And this is how they evolve, where this matrix A is evaluated as the Jacobian matrix evaluated along the reference trajectory. And just showing the form that A has, it looks like this in the circular restricted three-body problem, the 3D one. So A is a 6x6 matrix, but you could break it up into a block diagonal form where you've got a block of zeros, the identity, twice this matrix, which is just taking into account the velocities, and then this U matrix, which has all these second derivatives of the effective potential. And all of this is evaluated along the reference solution. The solution of the variational equation is known to be given by a state transition matrix. So if I have an initial variation at some time t naught, this multiplying that by the state transition matrix from t naught to t gives me what the small variation is after the elapsed time. So it gives the sensitivity of the state at some final time t to initial perturbations or displacements at t naught. And this is the ODEs that we get for now the 6x6 state transition matrix. Right? Phi is big. Phi is 6x6, so that means it's got 36 entries. So the ODE that you solve is this, where the initial condition is the 6x6 identity. You do this at the same time, typically, as you're following the actual trajectory. So what we have are these 42 ODEs. These are 6, and then these are 36, where the initial condition, you have some initial condition, but usually comes from an initial guess from that Richardson approximation. And then the initial condition for state transition matrix is just the identity. And what are we going to get? Well, you could use methods for doing differential correction. I'm now going to talk about, once you've found a periodic orbit or something that's periodic within some tolerance, what are the dynamics around the halo orbit? And to do that, we need to get that monodromy matrix. So that's the state transition matrix along the periodic orbit, following it for one period. Right, this is just restating that. So we're getting the monodromy matrix, which is this matrix here. So it follows it looks at how do small variations evolve over one period. And what we've done before is we look at the eigenvalues and the eigenvectors. So now, because M is 6x6, we have 6 eigenvalues to look at. So the first two, let's say we could group them in terms of pairs. The first pair, lambda1 and lambda2, are real, where at least for Sun-Earth Lagrange points, lambda1 is much greater than 1, around 1500, and then lambda2 is 1 divided by 1500. So these two are associated with the saddle type character of the halo orbit. So there's a direction along which things are leaving, and that's going to be related to the eigenvector that belongs to the eigenvalue lambda1. And then there's a direction along which things are approaching. So that's a contraction or stable direction, and that's going to be the eigenvectors corresponding to the eigenvalue lambda2. So that's similar to what we had before for the Lyapunov orbits. There's now a second pair, and this is also similar to the Lyapunov orbits. The second pair, they're both equal to 1. So we have 2 eigenvalues 1. So an eigenvalue 1 of multiplicity 2. You could think of it this way. The first eigenvalue is associated with variations along the periodic orbit. So if I have some kind of periodic orbit, and I have a variation along it, so some kind of perturbation delta x. Because it's along the periodic orbit, it's not really going to grow. It's going to stay the same. And that's what this one means. It means that that periodic perturbation, say after one period, isn't going to grow. It's going to just stay the same in magnitude. The other eigenvalue 1 is associated with if you did a variation to nearby energy surfaces. And on nearby energy surfaces, so let's say this is our halo orbit at a particular value of the energy. Well, at some other value of the energy, there's also going to be a halo orbit. There's actually a whole continuum. So this is just a schematic saying that at each value of the energy, there's going to be another halo orbit, especially infinitesimally small perturbations. So if you perturb, say, in that direction that points towards the other energies, you'll be on another halo orbit. And so that perturbation isn't going to grow. It's not going to grow or shrink. It's basically going to stay the same because you'll have, you're looking at displacement to a periodic orbit that's basically just shadowing what the original periodic orbit's doing. So the eigenvector corresponding to this other eigenvalue is just pointing towards nearby energy surfaces. So that's the second pair. Now, the third pair, this is new because of the spatial problem. So we didn't have this when we looked at the planar problem and Lyapunov orbits. The third pair are two complex conjugate eigenvalues of modulus 1. So that means, all right, if we're looking at sort of the real and imaginary parts, there's a modulus 1, and these two are just complex conjugate pair on the unit circle. And this corresponds to motion that is, in some sense, orbiting around the periodic orbit. So it's related to rotation around that halo orbit, or we call these quasi-halos. So you could have motion along the halo, and then this sort of spiraling that's related to the quasi-halo. All right. If you wanted to get onto one of these halo orbits, once you've found it, then one thing to do would be to calculate the stable manifold and integrate backwards. So calculating the stable manifold is very similar to what we already did for the Lyapunov orbit. So you have some point, you've got a periodic orbit, and let's say at some point along the periodic orbit, let's call that x naught, there is a stable direction. I'll call that ys. So that's the stable eigenvalue. You start with some displacement that's really small, and I say, epsilon of where the position projection would be about 200 kilometers. That seems to be, by a rule of thumb, that seems to work. And plus or minus, if you do plus or you do minus, that will give you an initial condition that's on either one branch of the stable manifold or the other. And then you just take that initial state, let's call it XS, and then you can integrate backward in time. And that'll give you a trajectory which is on the stable manifold. So if you then integrate forward in time, you'll get onto the halo orbit. And you could do this at different points along the halo orbit. So I'm showing here, this is showing a halo orbit in this figure, and all of the green arrows, the green vectors attached to the halo orbit, those are the local stable directions, at least projected into position space, because these stable directions are 6-dimensional vectors. So they have a direction in position and a direction in velocity, but we're just showing it in position here. So if you have, say, x naught, then you can look along a small bit along the stable manifold, integrate that backwards, and you get this red trajectory. If you wanted to get something at another point, let's call this x of t, then you could get what the stable direction is corresponding to that point just by using the state transition matrix. So this is the stable direction at x naught. This is the stable direction at xt, and they're related because these are both infinitesimal vectors attached to the periodic orbit. They're related through this state transition matrix. So it takes you from that initial time, let's say t naught, up to time t. So phi t from t naught. So if you integrate backward from multiple points, then you'll start to see this thing that looks tube-like. So here are some trajectories coming from a Sun-Earth halo orbit, and we're only looking at the ecliptic projection and how many of these seem to come back close to the Earth. So you could pick the one, let's say this is Earth, and maybe I'm trying to get to some desired orbit. I would pick the one that is tangent to that orbit, and then I would do a burn there, and then that'll take me just naturally onto this halo orbit. Easy peasy. Well, maybe not. If you do that, you'll get something like this. This is showing a halo orbit and a bunch of trajectories on the stable, on one stable branch and one unstable branch. So I'm showing the stable in green and the unstable in red. So I think this is Sun-Earth L1. You can kind of see the three-dimensionality. Sorry that it looks kind of, the frame rate isn't looking so good there. And then here's another video that we've made. So this is a halo orbit, and we'll show the entire sheet of trajectories. But this is just made up of a bunch of individual trajectories, and then we picked one that seemed to go to the Earth. And we go back, and you can see the individual trajectories on this stable manifold. Things are exaggerated here, like the Earth really isn't that big, but you'd want to pick the part of the halo stable manifold that comes close to the desired Leo orbit, and then you just do one burn, and this would take you onto that orbit. All right, I'm going to show some MATLAB stuff. I did want to show you some kind of foundational papers that are good for understanding the halo family. John Breakwell was a professor at Stanford who did a lot of work in this area. So he's got this paper from the late 70s looking at halo orbits in the Earth-Moon system. And they even find this set that they call the almost rectilinear orbits. I'm gonna just find those, because the almost rectilinear are the ones that one of those is being used for the CAPSTONE mission. So this is showing kind of a sideways view, and then the top view. A big contributor to this area now is Kathleen Howell, and I think she was a student of Breakwell. So this was a paper she had from 1984 looking at the almost rectilinear halo orbits. And you could see, people used typewriters back then. So the almost rectilinear are the ones that are almost vertical. So this is a sideways view, and you can see this is for L3, but you get something similar for L1 and L2. So you could look at those. All right. Is there anything else? This is just showing another mission that went to, in this case, L1. This was called the SOHO orbit. I think this was an ESA mission. All right. So I'm going to end just by showing some MATLAB code, and I'll provide this too, but just to give you an idea of how to use it. So this is called CR3BP _ halo _ manifolds. And I've got some global variables I have to define. I'm going to use for the mu for the Sun-Earth system. So this is, when you do things for Sun-Earth, you often include the mass of the moon in with the Earth. And so that's why I get this number, around 3.0359 times 10 to the negative 6. And here's an example of how to use this halo generation MATLAB code. So we'll pick, let's say that the L point will be L1, and then we need to set the Z amplitude. We're going to be calling a function that gives us the Richardson approximation. I think halo guess ANL stands for analytical. I'm just going to pick a Z amplitude that's kind of small, 0.05 in these units of the L1 to Earth distance. So L1 to Earth is about 1.5 million kilometers. So 0.05 is 75,000 kilometers. We can choose whether it's a northern or southern halo. And then this calls a function that just evaluates the Richardson approximation at a single time. So we don't really care about the whole trajectory. We just want an initial condition. And if we wanted to see how well this does, we can integrate it. So this just calls an integration function and then plots. So here it is. And I plotted, I think I did I don't know if I did forward or backward. I think this is actually forward. Type forward integration. And then let it go. Yeah, so this is going forward because the orbits around L1 and L2 are clockwise. So this is something that is definitely not periodic, right? It starts on the x-axis and then it hits the x-axis again, but it's not coming back up. It seems to go towards the moon's orbit and whatnot. So it's not perfectly periodic, which means we need to fix it. So we'll use differential correction to get a better approximation. I'll call this function called halo get. It's got different cases. In this case, it's going to keep the initial z value constant, but then vary two other things, the initial x and the initial y dot. If you were to run this in real time, you'd see the successive iterations. This took 5 iterations before it was able to get something that, so we're starting here, and this is computing something that will cross the xz plane exactly perpendicularly, meaning it only has y velocity. So all the other velocities are below some tolerance. So this is the initial condition it spit out. And there's the period in the usual non-dimensional units. So notice this is a little less than pi. So 2 pi would be 1 period of the Earth around the sun, so 1 year. So this is a little less than half a year. And so that gave us an initial condition and the half period. So now we'll integrate for a full period. So that's 2 times that half period. And you can see, here's the differentially corrected halo orbit. I don't know if this is 3D. Yeah, I think so. Can I move it around? Yeah, so you can kind of see, here's what it looks like from above. This is a L1 halo. And I view it as like the edge of a potato chip. It does have some curvature. Seen from the side, it just projects to a line. And maybe that's all this wants me to do right now. If you were to see it from Earth, you'd see this. The initial condition that I integrated is the red dot there. And so it's called a halo orbit because seen from Earth, it would, it seems to trace a halo around the sun. So Robert Farquhar was, I think he discovered halo orbits, and so he named them that. I'm just showing the same halo orbit, but now we're looking at, you've got the 3D, but then 3 different projections. So this one is you'd call this northern halo. So there's a mirror image solution too, which would be a southern halo. And once you've found the northern one, you can get the southern one just by applying some symmetries. So now that we've got this periodic orbit, now let's compute the stable manifold. I'll just pick one point. I've got some syntax here for this fraction. This fraction is, you need to pick a number between 0 and 1, and it's basically picking some fraction along the orbit between 0 and 1, saying, well, use that as your initial point for finding the stable manifold. So I picked some point that was at 0.9. So I think looking down here, this would have been 0, and then this would be 0.5. Apparently this is 0.9. So this is showing the stable manifold integrated backward in time. So if I started at this point and integrated forward, I should get something that goes exactly onto this periodic orbit. So that's just picking one point. You could show tick marks. So I've done something here where I'm showing tick marks of one day, and this gives you an idea of, right, when we're really close to the Earth is here. The distance between tick marks is large, meaning we're moving quickly. But on the halo orbit itself, things are moving pretty slowly. And now let's show several trajectories on the stable manifold. So there's some code, but here it is. So I've plotted, I think these are 50 different trajectories along the stable manifold. I don't know if this is going to turn. Okay, it kind of turns. And then the one that I showed before is in red. It's just one part of this stable manifold. We view it from above, you can kind of see. So if we were trying to pick something that had a close approach to the Earth, we probably wouldn't want to pick that red trajectory. We'd want to pick something else that gets closer. In fact, you can pick the size of the halo orbit so that the stable manifold comes exactly back to the LEO orbit you want. Maybe your LEO orbit is 250 kilometer altitude. You can make sure you find something that comes back to 250 kilometer altitude. And then you just have to do one delta V there, and then you get a natural transfer onto a halo orbit. Is that it? Yeah, so that's what this code does. And you could play with it if you want. We can go up here and change it to be L2. What was it? So if I wanted something that's more like the James Webb, I can make this Lagrange point 2, and then instead of 75,000 kilometers, maybe I want something closer to 300,000. So that would be this non-dimensional units 0.2. And I'm just gonna run this and see if it works. Is it thinking? Yeah, it's thinking. Okay. So here it found some initial guess. It's a lot better than me just trying by hand. So using this Richardson approximation, it at least crosses the x-axis once. And that's why we've set up the differential corrector to work with that. You want to make this another perpendicular crossing. So you can do differential correction, and here is that differentially corrected thing up to half a period. And then the other thing comes from just mirror symmetry. Here's that entire orbit differentially corrected. This is around L2. And I think this is a southern halo. I've got the 3D and then different projections. So if you recall what the James Webb looked like, it kind of looked like this. So L2 is there, L2 is there. So it's pretty close to the James Webb one. Yeah, this is a branch. I'm using the same things here. So maybe I'll do -1 here. And this will give me a part of the stable manifold that doesn't come from the exterior realm, it'll come from the Earth realm. So I just change this from a plus to a minus. And then if I rerun, I'll get the other branch, so it should be going towards the Earth. And this is in backward time. There we go. Let me let this integrate for a little bit longer. So I went from 0.6 to 0.8 times a year. So 0.8 of a year, what is that? That's a bunch of months. Okay. There we go. We get something, does that. If we change this number, let's say instead of 0.9, if I did 0.8, this will be, it'll pick, instead of this point along, they'll pick some other point that's along the halo orbit and give us something on the stable manifold there. Oh, okay, good. I'm noticing that this is getting closer and closer to intersecting the Earth. Like, I think I have this set up so that we could, this is the actual size of the Earth. So this is a circle with a radius of 6,378 kilometers. But this is in units. We're writing everything in units of AU. Just all right. So you could add tick marks. You could show the whole manifold. So this is showing. Kind of got something weird going on here. Maybe I'll make this go 0.99, 1.013, something like that. Sometimes it's hard to set the axes to make things look nice. But this is part of the stable manifold that leads to that James Webb. So if you wanted to, you could probably try to redo what they did for James Webb. Now, this is in the circular restricted problem. So we're really getting onto a truly periodic orbit. In the real ephemeris, it's not going to be exactly periodic. It's going to be pretty close, but there's the effect of the moon and things that will kind of mess things up, make it not exactly periodic, but the circular restricted three-body problem is still a very good initial system to look at. So this gives you an idea of the tangle of spaghetti that comes from these stable manifolds. Okay. So, like I said, I'll provide this code so you can play with it. There's a lot more that could be said about the three-body problem, but that's all we're going to say for this short course. And hopefully it's been valuable for you. So thanks for hanging in there. If you want to know more of the details, this is from chapter 6 of the book. So look at chapter 6. And then the other chapters go on to other topics like end-to-end transfer design, using the three-body problem as a building block for designing four-body problem trajectories. And then I think that's it. See y'all later. Hey, if you appreciated this course and you'd like to see more advanced level content like this, please like and subscribe.